So, we have seen invariance properties of the Lebesgue measure, we have seen finer properties of the measurable sets. We have proved that the Lebesgue sigma algebra is the completion of the Borel sigma algebra with respect to the Lebesgue measure. Now, we will continue with the measurable functions and see some more finer properties. So, recall that we started the course with abstract integration, abstract measure theory and so on, where we had defined measurability of functions and we looked at integrals and so on. So, we will make some of those results finer using the extra structure on Rn. So, that is what we will do first, and then we will compare Riemann integrals with Lebesgue integrals. Okay, let us start. So, measurable functions. So, we know what they are. So, let's recall that. So, side on the side. So, if I had a triple x f mu, right, this was the abstract setting, x was a space, f was a sigma algebra and mu was a measure. We said a real valued function or a complex valued function or sometimes it was minus infinity to infinity and so on. This is measurable if f inverse of a Borel set was in the sigma algebra we are interested in, right. So, this was a Borel set. So, B belonged to Borel sigma algebra of R or Borel sigma algebra of C and so on, which was equivalent to saying f inverse of an open set is open set belong to the sigma algebra. That will do. So, recall that, and then that is the definition of measurable functions now. So, if I have a function f taking values in the real line, the complex plane, or it can, remember, it can take minus infinity and plus infinity and so on, that is allowed. Appropriately we change the sigma algebra. Then f is measurable if f inverse of a Borel set belong to the Lebesgue sigma algebra of Rn. So, this is the one you should keep in mind, because the right hand side has a Borel sigma algebra, B Borel. So, whenever we pull back a Borel set, we should get a Lebesgue set. Okay. So, that is what you mean by a measurable function. If we put a restrictive condition that f inverse B actually belongs to the Borel sigma algebra instead of the Lebesgue sigma algebra, then we say f is Borel measurable. Okay. So, f is said to be Borel measurable. So, again f is defined on Rn, let us say to R, if f inverse of a Borel set B belongs to the Borel sigma algebra. Okay. But here it is when we say measurable, so you can say Lebesgue measurable if you like, but I will simply say measurable. So, whenever we say measurable, the underlying sigma algebra is the Lebesgue sigma algebra. Okay. All right. So, that is one. A step function. So, this is again using the structure of Rn. Okay. In the general settings, when we looked at the triple x f mu, we had simple functions. Which makes sense here as well. Okay, whether it is on Rn or capital X does not matter, we have simple functions always, but step functions use the structure of Rn. Just like on the real line we know what step functions are, right. These are linear combination of indicator functions of intervals. So, intervals will be replaced by cubes. So, a step function S is a measurable function. Well, it will be always measurable because we are looking at the cubes. S is a function which is given by a linear combination of finite linear combination of rectangles, okay, or cubes. So, finite, okay, where Rk are rectangles. So, this is of course measurable, Rk are rectangles. So, in the real line this would be a usual measurable function, usual step function, right. So, if I look at the real line, a rectangle is an interval, right. So, you have one interval, you may have a bigger interval and so on. You fix a constant here, you fix another constant here, that is your step function, and this is simply the generalization to Rn, but that uses rectangles, right. So, it's defined only on Rn. So, these are of course simple function, okay, a step function. So, step function is a simple function as well. Step function is a simple function as well. But the converse is not true, because simple functions can be linear combination of arbitrary measurable sets, indicator of arbitrary measurable sets. The measurable sets need not be rectangles, right. When they are all rectangles, we say it is a step function. So, that is a smaller collection of measurable functions, right. So, this is one of the finer properties of measurable functions on Rn, because we have extra structure. So, let f be a measurable function. So, recall that whenever we say measurable, we mean Lebesgue measurable, and when you pull back Borel sets, you will land in Lebesgue sigma algebra. So, that is what is meant by a measurable function, measurable on Rn, okay. It can take complex or real values. Then there exists a sequence of step functions, okay. We will call that psi k, such that psi k converges to f almost everywhere. So, remember we had in the general setting, in the abstract settings, we had simple functions converging to f almost everywhere. Those simple functions can be modified to get step functions, right, because this is the structure of Rn which we are using. So, proof of this is not very difficult. So, from the abstract theory, we know that there exist simple functions, there exists sk converging to f, sk simple, right, this we know. Each sk is a linear combination of measurable sets, right. Well, maybe use L here just to, where El is a Lebesgue set. So, to show that any measurable function can be approximated by step functions, it is enough to look at indicator of a measurable set and prove that it happens for such a set. So, enough to show that indicator of E, where E is an arbitrary measurable set, can be approximated by step functions. So, this is where we will use the finer properties of Lebesgue sets which we had proved earlier. So, if you can approximate indicator function of an arbitrary measurable set by step functions, then using the general theorem we can prove this for any arbitrary measurable function. So, that part I will leave it to you. So, we will just prove that any set E with if I take an arbitrary E in L of Rn, chi E can be approximated by step functions, okay. Well, how do we do this? We use one of the results. So, let me recall this result, recall that there exists. So, we may assume before we go further, we may assume that assume that measure of E is finite. Okay, so that's a easy exercise. Let me, okay, suppose measure of E is finite, infinite, okay, then I can cut it down by balls, right. So there exists En, okay, such that measure of En is finite and chi En will converge to chi E almost everywhere, right. What do? You simply take En to be E intersected with ball of radius n, okay. So then it becomes bounded and it has finite measure, okay. So I can assume measure of E to be finite because that is enough because of the exercise. Now once measure of E is finite, we know that it can be approximated by finitely many cubes, right. So by an earlier result, for every epsilon positive there exist finitely many cubes, right, Qj. So let us say j equal to 1, 2, 3 etc. capital N, such that E can be approximated by these cubes, which is same as saying the measure of E delta, the symmetric difference union j equal to 1 to n Qj is less than epsilon, right. So this we had proved, this was one of the finer properties of the measurable sets we had proved if the measure of E is finite. So these cubes, well, so let us say these cubes are like this, we don't know how they look like, so some cubes, so this may be, one may be here and so on. So this is how the picture looks like in, let us say, R2. What you do is you extend the sides of the cubes, okay, like this. So you get a grid on Rn, okay, where we had so the cubes are here. So let us say this is Q1, this is Q2 and this is Q3 and so on. Okay, so we have these cubes, you form a grid by extending the sides. So consider the grid formed by extending the sides of the cubes Qj, okay. So then if you look at these grids, you see that you get one rectangle here, you get another rectangle here, right, and so on. Here another rectangle, here another rectangle, and such, here another rectangle and so on. So each of these cubes can be written as union of rectangles and they are almost disjoint, okay. So if you look at the picture, this will be very clear, so but let me write it down. We get that the union of Qj, j equal to 1 to n, equal to union of j equal to 1 to some other number m, but finite, Rj tilde, where Rj tilde are almost disjoint rectangles, okay. So the Rj tildes are here. So this would be one of them, this would be another one, this is another one and so on. So if you have cubes and if the cubes are already almost disjoint, then the extending the grid does not divide the cubes again, right, but the cubes may be overlapping, right. So if I have two cubes like this and if I extend the grid, I am going to get something like this, right. So that will give me this rectangle, this rectangle, this one, this one, this one, this one, and so on. So several of these rectangles, but almost disjoint, and the original cubes are union of almost disjoint rectangles which we have just constructed. Choose smaller rectangles Rj contained in Rj tilde. So when I say smaller, I don't mean very small. So this would be, let's say, slightly smaller. Okay, slightly smaller rectangles Rj contained in Rj tilde, such that the measure of E symmetric difference between Rj, j equal to 1 to m, this is less than 2 epsilon. That is possible, right, because the union Qj is same as union Rj tilde, and union Qj give me an epsilon difference at the most. So if I shrink the Qj's, the Rj tildes, then I will get Rj's such that the maximum difference between them is of measure less than 2 epsilon. That is possible. Okay. So hence, if we look at indicator of union Rj, j equal to 1 to m, remember they are disjoint, right, they are almost disjoint. So this is same as summation, right. If I have two almost disjoint rectangles, let us say R1 and R2, the indicator of R1 union R2 is equal to indicator of R1 plus indicator of R2. Well, of course, if they are equal, if R1 and R2 are disjoint, but if they are not disjoint, on this line you add twice, but that line has measure 0. So this is equality almost everywhere. So this sum would be indicator of Rj, j equal to 1 to m, but this may hold only almost everywhere. If they are truly disjoint, of course the sum is an equality, but otherwise they agree on the boundary, but the boundaries have measure 0. So this is something you should convince yourself. I had done these examples of computing the measure of lines and so on, which gave me 0. Similarly, the boundary of the cubes will have measure 0. Okay, so this tells me that, so using the equality 1, the indicator of E will be equal to summation j equal to 1 to m indicator of Rj, except on a set whose measure is less than or equal to 2 epsilon, right. So given any epsilon, I can find rectangles, almost disjoint rectangles, and the sum of their indicators like this, so that the indicator function is same as the sum of the indicator function of rectangles, except on a set whose measure is less than or equal to 2 epsilon. So we use this to produce the convergence. So remember, we want to prove that there is a sequence of step functions converging to the measurable function, right. So we need to get step functions. What we have done is to approximate this up to 2 epsilon. Now you run epsilon over 1 by k, right. So hence for each k there exist step functions psi k such that, so now we have step function, right, because we are taking in indicator of rectangles and the linear combinations of that, such that the set Fk where they differ, right, x, such that f of x is not equal to psi k of x. So remember, f is the we are assuming f to be the indicator function of E, right, where they are not equal has measure small. So measure is less than to, let's say, 2 to the minus k. So, because we can do this for every epsilon, we do this for epsilon equal to 2 to the minus k as k runs over 1, 2, 3 and so on. Now consider f to be the lim sup of these fk's. Lim sup of fk. What is lim sup of fk? You look at the intersection n equal to 1 to infinity union j equal to n to infinity fj, right. You look at the union from nth space on nth place onwards and take the intersection. This is called the lim sup. Well, exercise, this is pretty easy. Measure of f is 0. Okay. Well, this is easy because measure of union j equal to n to infinity fj. This I know is less than 2. By subadditivity j equal to n to infinity measure of fj, but measure of fj is less than 2 to the minus j. So, I have j equal to n to infinity 2 to the minus j, and this you can add by geometric sum, right. So, this is like 1 by 2 to the n minus 1 or something like that. And then you are taking the intersection. So, intersection gives me a decreasing sequence of sets, and the measure theoretic results you already know will tell me that there is convergence, right. So, if I call these sets an, then an's decrease to lim sup of fj. Okay. So, measure of an should decrease to measure of this, but measure of an is bounded by 1 by 2 to the n minus 1, which goes to 0. Okay. So, that is easy. Well, so this is the set. So, what are fk's? Fk's are the sets where it is whatever we want is not happening, right, but the lim sup of that is 0. So, outside f, so this is, you can complete the proof by observing that the measure of f equal to 0 and on f complement, that is the complement of the lim sup set we have just constructed, convergence takes place. Convergence take place. What is convergence? So, the psi k which we have constructed, psi k are step functions, right, psi k which is not equal to the indicator function, that set is fk, but we are outside fk when we look at f complement, convergence takes place. So, psi k becomes f. So, f remember is chi as k goes to infinity, but f is such that the set capital F is has measure 0. So, this is same as saying psi k converges to f almost everywhere. Okay. So, any Lebesgue measurable function can be approximated by step function. So, approximating by simple functions is the general theory. Because of these properties we have step functions. Okay, so that concludes the finer properties of Lebesgue measure, Lebesgue sets and Lebesgue functions. But now, so now we have the Lebesgue theory of integration. We want to compare it with Riemann integration. We want to say that Lebesgue integral is more general than Riemann integral, in the sense that if the function is Riemann integrable, then it is also Lebesgue integrable and the integrals are same. So, that calls for a comparison between Lebesgue integration and Riemann integration. So, let's start with the preliminaries, and in the next session we will complete the proof. Okay.